10 is about rotational dynamics. Chapter 9 talked about how things move. Chapter 10 is why things move. In linear motion, if we want to change something's motion, we need a force. In rotational motion, if we're going to change something's motion, we're going to need a torque. So torque plays the same role in rotational motion that force played in linear motion. We define torque as that tendency of the force to change an object's motion. So we still need a force, but it's not quite that simple. The formula for torque is force times the lever arm. And I say lever arm, actually the correct word is, this is a moment arm. Okay, so we need to define where that moment arm is, and then we are going to bring up the idea of a lever arm, which is actually a little more practical, a little easier to use. Suppose we have some arbitrarily shaped solid object, doesn't really matter what it looks like. We want to rotate it about its center, or about some point, not necessarily the center, but we're going to have an axis right there. We want to rotate it. We apply a force right here. This line right here is the line of motion. The moment arm would be this right here. That perpendicular distance, that's L. Now, a lot of times it's easier to simply measure how far is it from where I exert the force to where this center of rotation is. I'm going to draw that in a different color. I'm going to label that R. R is something we call the lever arm. You want to rotate it about this point, you apply the force right there. In terms of the moment arm, if we think about the angle between the force and the lever arm, so the force is applied along this line, this angle right here, I'm going to call phi. If I want to get L, look at this right triangle here. Let's use the trig function for sine. Sine phi, remember, sine is opposite over hypotenuse, so in this case, opposite would be L, the hypotenuse would be R, and we realize that L is equal to R sine phi. This brings us to another formula, and probably one that we will use even more than this. So if this is our definition for torque, that can also be written as torque. Notice this is a Greek letter tau, that's why it's kind of a curvy looking T, is equal to F R sine phi. And phi is the angle between the direction of the force and the lever arm. One thing that's really nice about this is it really doesn't matter whether you use the acute angle that's formed or whether you use the obtuse angle that's formed, because they're going to be the same measurement. The sine of 30 degrees is the same as the sine of 150 degrees. So we could have used this angle between the force and R, or we can use this smaller angle that I drew between the force and R. We haven't talked about a unit yet. It does have a unit. Since the SI unit for force is newtons, for any distance it's meters. So the SI unit of torque is a Newton meter. If we look at this, we can see that we're going to get the largest torque when the angle is 90 degrees, which is pi over 2. That gives us a maximum torque. Sine 90 is 1. That's the largest sine will ever be. There will be no torque at 0 degrees, or for that matter at 180 degrees. That will give us a torque that's equal to 0. All right, let's look at some things that maybe are a little more practical. This is all a little bit theoretical. Just kind of expand this. One of the simplest examples of a torque is opening and closing a door. I don't know if you've ever thought about it, but there's a really good reason that the door knob is on the side opposite the door hinges. If you try to close a door by pushing really close to the hinges, it takes an incredible amount of force, much more than you probably realize. Picture of the door. If the hinges are over here, hinge, 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 and the doorknob is here, you essentially have a lever arm that long. Notice the longer L is, the greater the torque. If it takes a certain amount of torque to open and close that door, the longer L is, the less force you're going to need. Or if you looked at it from above, if here is the hinge. Also, the easiest way is to keep this angle at 90 degrees. If you want to push the door, it's easier if you push it directly at 90 degrees. If I want to open or close this door, if I come in here and I push at this angle, here's my lever arm. If F and L are in the same direction, I will accomplish absolutely nothing. I cannot close the door by pushing on the outer edge of it. If I need to close or open, I'm not sure, it doesn't matter which. I need to push perpendicular to the lever arm, or at least some component has to be perpendicular to the lever arm. While we're thinking about it, notice the way I've drawn this picture. This would have a tendency to rotate that direction. Counterclockwise, and that's how we normally abbreviate counterclockwise. Counterclockwise torques are positive. Clockwise torques are negative. That makes sense because that's in keeping with the same way that we measure angles. We know when we measure an angle, we start at the positive x-axis and counterclockwise is our positive direction. All right, let's work an example. Well, let me draw one picture. So, for example, if I have a disc and I want to rotate this disc about the center, if I apply a force right here so that it's tangent, here's the radius, that torque will be equal to Fr. But you'll notice it will make the object tend to rotate clockwise. So this is going to be a negative because it's clockwise. It's really a decision we just have to look at and make. We don't think, oh, I'm applying a negative force necessarily, but I do generate a negative torque. On the other hand, if I applied some force down here or over here, let's put it right here. Also, a distance r, make those two perpendicular. That right angle just means we're getting maximum torque. If that first torque caused a clockwise rotation, a torque here would be a positive because it would make it want to rotate counterclockwise. To get the net torque, we would simply add up all the torques, all the positive torques and all the negative torques. In this case, it would depend which one was larger. If F2 was larger, the net torque would come out to be positive. If F1 was larger, the net torque would come out to be negative. If they were equal, the net torque would be 0 and the object would not rotate. This is example 10.1. And in this problem, it says we've got a plumber who's unable to loosen a pipe fitting. So he uses a piece of pipe as a cheater. A cheater basically just makes you have a longer wrench. You know, all wrenches have a handle that acts as the lever arm. So in this case, I'm going to draw the picture. There is a pipe fitting up here. They do it kind of hexagonal. And he's got a wrench that he's got hooked on it. So there's the wrench. Not drawn perfectly, but you get the idea. He can't budge it. So he takes this piece of pipe and slides it on. And now all of a sudden he's increased the lever arm. Here's the center of rotation. The distance from where he's going to apply the force. I'm going to extend my picture just a little bit. He's going to apply the force right here, straight down. And that distance from where he applies the force to the center of rotation, that's our lever arm, that's R. The distance from where you apply the force to where the center of rotation is, that's your R. They tell us in this same picture that this is a 19-degree angle. If you were to extend this out. Okay, what does that mean if that's a 19-degree angle? Well, think in terms of a triangle. If that's a 19-degree angle, then this is a right angle, then this angle up here, 90 minus 19, must be 71 degrees. So I had to do a little bit of figuring to figure out what's the angle between the force and the lever arm. The other option is I could use this larger angle here, which would be 109. 71 and 109, they're going to have the same measure. I just need the angle between the force and the lever arm. So, what's the torque? It says that he stands on the end of the pipe applying his full weight, which happens to be 900 newtons. So this man weighs 900 newtons and he's going to stand on it. This distance from F to this, it said was 0.80 meters. And of course he's not perpendicular. It's not going to apply quite his full weight, but almost perpendicular. 71 degrees. There's a little bit of an angle. So he's coming in at 71 degrees. Put that in a calculator. To 2 digits, it came out to be 680 Newton meters. All right, if he's stepping on it down here, notice it's going to rotate this way. That is counterclockwise, so that's a positive torque. Or you can just say counterclockwise. The second part of this problem says, if the maximum torque that this particular pipe fitting can tolerate is 100 Newton meters, so if we use more than 100 Newton meters, we're going to break this off. That is a problem for plumbers and handymen everywhere. You can't put too much torque. Things will just break. So the max it can tolerate, it says, is 1,000 newtons. It says, what's the longest pipe he could use? Okay, well, if the maximum torque allowed is 1,000 newtons, and he's still using his full weight, and he's still applying it in that same direction, that's just solving for R. If we solve that for R, it comes out to be 1 point, again, I think we'll stick to 2 significant digits, 1.2 meters. Okay, so torque causes rotational motion. See, just like force can cause translational motion. So if a force can cause a translational or a linear acceleration, it makes sense that torques can cause a rotational acceleration. Brings us to the next section in our book. We know that the sum of all the forces, which is another way of saying that the net force, is equal to mass times acceleration. That's Newton's second law. Our rotational equivalent says that if we have the sum of all the torques, or the net torque, that will equal not the mass, but the moment of inertia. When we're talking about rotational motion, it's not the mass that's significant, it's the distribution of that mass in which we use the moment of inertia to describe. So this is I. And of course, we're talking about rotational acceleration. So that's alpha. All right, let's look at a problem. We did this problem, I believe, in the previous chapter, but it was a slightly different question that we asked. We had a disc. There's the center of the disc. It weighs 50 kilograms. It has a radius of 0.06 meters. We're going to apply a force right up here. of 9 newtons. And our question simply says, what is the magnitude and direction of the angular acceleration? In other words, find alpha. Okay, it's a disk. We're going to need its moment of inertia. We're going to need the torque because we're looking for alpha. Well, the torque's pretty easy. The lever arm in this case is where is the force applied? It's right there. What's the distance to the center of rotation? It's right there. So, and this is at a 90-degree angle, so our torque is simply 9 newtons times 0.06 meters. That comes out to be 0.54 Newton meters. So torque was not a problem to find. It's obviously counterclockwise. So any rotation caused by this torque will be counterclockwise. The moment of inertia for a disk is 1/2 mr squared. So for this disk that weighs 50 kilograms and has a radius of 0.06 meters, 1/2 mr squared, it came out to be 0.09 kilogram meters squared. So we have our torque, we have our moment of inertia. We can just put that all in this formula. 0.54 Newton meters equals 0.09 kilogram meters squared times alpha. And alpha is going to come out to be 6.0 radians per second squared. Now, if I want to find the acceleration of the rope, remember this was a winch. If we actually go back to the original problem, we're pulling on a rope and we want to find out, well, if this is rotating with an acceleration of 6 radians per second squared, what's the linear acceleration of this rope? The linear acceleration, and this is a tangential linear acceleration, is simply r alpha. So 0.06 times 6.0 radians per second squared, and it comes out to be 0.36 meters per second squared. All right, they give us more to this problem, so I do want to do the rest of it, but I want you to think about this for a minute. Net torque, pretty straightforward. Force times the lever arm. The lever arm is the distance from where did I apply the force to where is the object rotating. Moment of inertia, that's just a straight plug it in. It's 1/2 mr squared. We know m, we know r, piece of cake. So getting alpha was really easy. And then understanding the rotation, since this is a point at the surface, at the edge, if we're pulling a rope and winding a winch, I believe is what they said we're doing, that the linear acceleration of this rope is directly connected to the angular acceleration. We have that formula. There it is. Okay. Part B says, hey, let's throw in another force, a second torque. What if there's something else right here that is a smaller force of 3 newtons? What's that going to do to our acceleration? Well, common sense says obviously it's going to slow our acceleration. I'm not going to erase all of this, going to erase right here. We now know that we have, we'll call this 1. Whoops. We have this initial force and this initial torque. We have a second force that's exactly 3 newtons. Make sure you can see that decimal. So the second torque is 3 newtons. It's also 0.06. That's going to be 0.18 Newton meters, but it's going to be clockwise. We're going to treat this as a negative. That means when I'm ready to get my net torque, it's going to be a positive 0.54 and a negative 0.18. That's actually going to be 0.36, and that has to equal I alpha. I alpha is 0.09, that's I, times alpha. This time alpha is going to come out to be 4 radians per second. I think we had 3 significant digits, so I'll put a third one. Radians per second squared. It's just like we were doing a net force. If we had 2 forces and one kind of opposed the other, like maybe a frictional force, the acceleration would be less. Well, if we have a torque that's opposing this initial torque, that could be a torque due to friction. I don't know what's causing that opposing torque. But in that case, we would look at the net torque, and the net torque still equals I alpha. I didn't change, but alpha had to change. Okay, so we have one more idea we want to talk about in this video, and that's the idea of work and power. We want to talk about the work and power. Let's go back to what we know about linear work. Linear work is a force times a displacement. Now, the force and the displacement have to be in the same direction, but that's essentially what it is. So from rotational motion, work is simply a torque times an angular displacement. You can see the corollary. Instead of forces, we use torques. Instead of linear displacements, we use angular displacement. Power, of course, is work over time, or if we're thinking linear, this can also be written then as power equals FV. If we're thinking rotational, power is still work over time. That can be written as work over time, in which case power would become the torque times the angular velocity. The unit in both of these cases is joules, and these of course will be in watts. Next problem. Okay, I'm going to read this problem. I'm I'm sure it's in your book. It says, an electric motor, so an electric motor exerts a constant torque of 10 Newton meters on a grindstone with a moment of inertia of 2 kilogram meters per second squared. So they're telling me that my torque is 10 Newton meters and that my moment of inertia is 2.0 kilogram meters squared. You're not going to make me work out those two items. If the system starts from rest, find the work done in 8 seconds and the final kinetic energy. What is the power? Okay, so they're asking me to do a lot of things. They're telling me a little more. It starts from rest. And we're going to let our time interval equal 8 seconds. Here's the thing that they want us to find. They want us to find the work. They want us to find the kinetic energy. They want us to find the power. So, a lot of things to find. Okay? We know that work is the torque. That's force times displacement. In this case, it's torque times angular displacement. So I think the first thing we want to know is if this disk starts from rest, how fast will it be going if it has a constant torque? How many angles will it go through? We better start with what we have enough information to figure out. They don't tell me the angular acceleration, but they definitely make that one an easy one to figure out. If I use torque equals I alpha, and this is 10, and this is 2, then alpha must equal 5 radians per second squared. So I've gained another critical piece of information here that's going to help me solve problems. I have a constant torque, so I have a constant acceleration. All right. I really want to know that. So I think I'm going to have to go back to one of our original formulas and say, hey, if I start at rest and I have this much acceleration, how far will I rotate in 8 seconds? That looks like this. Theta equals theta 0 plus omega 0 t plus 1/2 alpha t squared. I want theta. I really want displacement, which is theta minus theta 0. So this displacement is going to be, well, omega 0 is 0. So it's just going to be 1/2 alpha t squared. That's 64. Half of 64 is 32. 32 times 5 is going to be 160 radians. In 8 seconds, if this begins at rest, it's going to rotate 160 radians. Whew, I think I can answer the first question. Let me write this down, just in case I need it. All right. Notice we haven't answered any of our questions yet, but one of the ways you successfully solve a problem is you find the things you know you can find. I know I can find alpha if I know the torque and I know the moment of inertia. I know I can find out how far something will rotate in 8 seconds once I know this acceleration and I know the time, I know the initial velocity. So now we can get the work. The work is the torque times the angular displacement, that's 160 radians. So our work is 1,600 joules. Pretty straightforward. Our kinetic energy is 1/2 I omega squared. Uh-oh. Let's see. It wants to know the final kinetic energy. There's two ways I can do this. I want to think about it. One way is I can find the final speed. Let's find the final speed. I know the final speed is the initial speed plus alpha t. So that's 5. The time was 8 seconds. That's going to be 40. If I use that piece of information, that's going to be 1/2 times 2 times 40 squared, and the final kinetic energy is 1,600 joules. These two are alike. It's not a coincidence. I didn't even really need to find the final velocity, angular velocity. It wasn't hard to find it. I mean, if I'm accelerating at 5 radians per second squared and I do that for 8 seconds, I'm going to end up going 40 if I started from rest, 40 radians per second. But I could have gotten this using work energy. The amount of work done, the net work, is your change in kinetic energy. If you do 1,600 joules of work, and that is the only work being done, that object's going to gain 1,600 joules of kinetic energy. It started with none, so the final had to be 1,600. Now, if it had started with 1,000 joules of kinetic energy, and you did 1,600 joules of work, it would have ended up with something 2,600. But in this case, it started with 0 because it was at rest. So you do 1,600 joules, you get 1,600 joules of kinetic energy. But we did it the other way, got the same thing. That's really important. Often in physics, there is more than one way to get the answer. And if you're doing it right, both ways have to give you the same answer. There's not but one correct solution, but there's probably more than one correct approach. Power. Last thing they want is power. Power, of course, is work divided by time. So if we do 1,600 joules of work in a period of 8 seconds, that is going to be 200 watts. All right, that's the first half of this chapter. Spend some time on it. I know these ideas are in some ways very familiar because they look so much like linear motion, but I also know they're not necessarily easier. Okay, the second half we're going to look at conservation of angular momentum.